Okay, this is the Hooke's law. It's slightly different to Hooke's law because of this negative sign. This is the equation. If you have an entity on a spring, this describes the restoring force of that entity. So basically, it's the force that is exerted on that entity. So this is not the force exerted by the spring; it's the force exerted on the spring. So it's slightly different. This is using Newton's second law. So the force is always exerted in the opposite direction and to the x-axis. So just think about this. This is the x-axis. If I'm moving in simple harmonic motion like this, the force that's exerted on me is always in the opposite direction to my displacement. So here the displacement's positive, and it's acting in the negative direction. Here the displacement's negative, and it's acting in the positive direction. So that's basically what's going on here. You can prove this using Newton's third law. It's exactly the same as Hooke's law, except for this negative sign. So again, fairly straightforward. Now I'm going to prove the relationship between angular velocity, and the spring constant, because there is a relationship. I'm going to show you that. I'm going to use vectors. Now, you can think of simple harmonic motion as actually being a projection. This entity here is moving around the circle, and the simple harmonic motion is the projection of this entity onto this x-axis, or you could say it's the component of the vector, on this vector. So it's in the opposite direction to the force, but of this vector onto the x-axis. So it's going. So as this goes round, this grey one is the projection, or you could think of it as a shadow. So now I'm going to construct some vector equations to try and show some relationships here. Centripetal force equation. So I've got this indicates that it's acting towards the centre of the circle. The mv squared over r bit is very simple. That's just from the centripetal force equation. I derived it in an earlier video, so I'm not going to go through that now. I'm going to touch on what the negative r over r modulus is here. I should note that anything in a modulus is not a vector. It's the magnitude of the vector. So basically, I've taken the vector and I've got rid of its direction and just kept its magnitude. Obviously, you can't divide by vectors. That doesn't make sense. So what I've done here, as I said, well, okay, r is vector from the centre of the circle to the entity. So I've drawn it here for convenience, but the entity would be here. So what I've said is, well, okay, the direction of the centripetal force is in the opposite direction to this entity here. What's going on is you can see that this vector is from the centre of the circle to where the entity is. But it's going outwards, and we always know the centripetal force goes inwards. So that's what the negative sign is. So negative r indicates that we've got a vector that's going in the opposite direction. Centripetal force is in the opposite direction to this vector here. The magnitude here, I've divided by this because obviously a vector contains a direction and a magnitude, and I've already got the magnitude that I want here. So dividing by it gets rid of this excess that I don't actually need. We know that the magnitude of the centripetal force is mv squared over r. So basically, I've multiplied mv squared over r by a unit vector, which is minus r over r. That's my unit vector. So I multiply it by 1 with a direction, basically. Okay, this is just using the relationship between linear and angular velocity, v equals r omega. Again, that's fairly straightforward. Notice that my angular velocity is also in modulus sense because angular velocity does actually have a vector, but it points in a surprising direction. It actually points out of the page. So I put this in modulus sense because I only want its magnitude. Otherwise, this equation would not make sense. So you can see that the direction of the centripetal force is still going inwards towards the centre of the circle. Okay, now I'm going to take the component of this force in the x direction. So this f here is basically the same f that I've got up here. So don't confuse these two f's because they're different. This is the centripetal force, and this is this one here is the restoring force of the spring. So they act in different directions. So that's why I put this in modulus again, because the direction is obviously not going to be in the direction of the centripetal force, because this only acts in one dimension, whereas this acts in two. But anyway, apart from that, I've got the magnitude of this force in the x direction, which I've just multiplied by cos theta to get it in the x direction. That's just a simple projection, very simple trigonometry. And again, I want the force to act in the opposite direction to the vector x, which is the one-dimensional version of this. So vector x is from this point here is my origin. So I want the force that's acting on this grey object to be in the opposite direction to its displacement vector. So that's why I've got minus x here, and then I've divided by the magnitude of x. Same principle as what I did here. Okay, so I've just substituted in the magnitude of the centripetal force, which is m omega squared r, and then x over r here is the cos theta. That's just trigonometry, so we know from right-angled triangles that this is going to be x over r. So that's simple trigonometry. Cos theta is equal to x over r. So yeah, these are all magnitudes, because we want to preserve the direction of the vector. It's in the negative x direction. So simplifying that, these two r's cancel, that x cancels with that x, so we're left with minus m omega squared and x. You notice that this vector here is just the vector x, so it's in the direction of the negative x direction. So everything's still checking out. So now what we're going to do is going to look at we're going to rearrange this equation for omega. Now you can't just rearrange a vector equation in the normal way as you can for a scalar equation, because you cannot divide by vectors. So don't even try to divide f by x, because it doesn't work. It's just nonsense. So we can't do that. So we're gonna change this vector equation into a magnitude equation. So I'm taking the magnitude of these vectors. I'm not taking the vectors themselves. That's to just avoid dividing by vectors, which is rubbish. So I've taken the magnitude of this as usual, and then I've said that that's equal to so I've got taken the magnitude of the force here divided by the magnitude of x multiplied by minus m, and then square rooted to get to rearrange for omega. Notice that again there's no vectors here. This is a scalar equation. So just a simple way of rearranging. Well, I've substituted the magnitude of f for minus kx, which is at the top here, although this is a vector equation and this is a scalar equation. So that equals the root k over m. So we've shown that the magnitude of the angular velocity is equal to root k over m. Now, if you wanted the actual vector equation for this, you'd have to do some. It would be slightly more complicated, because this vector actually points out of the plane. So this vector actually points out of the plane of the circle. So it's more complicated. So the equations get more difficult to deal with. So yeah, just a hint: never try and divide by vectors. It just doesn't work. Okay. Having said that, I'm going to look at a simple pendulum now. You've probably seen this relationship. It's quite simple. So now I'm going to derive the same thing for a pendulum instead of a spring. Okay, so for a pendulum, I've got fx equals minus mg sine theta. Then the negative. You'll notice that this is a scalar equation. There's no vectors and no arrows. It's just a scalar equation. The minus indicates that again, the force that's acting is going to be in the negative direction to its displacement. You notice that I say direction. It doesn't mean it's a vector. It's just acting in the opposite direction. You can still have a negative scalar. That still sort of indicates that it's opposite. I mean, in one dimension, the negative of something you could say acts in the opposite direction. But it's important to distinguish that this is not a vector. So this is mg sine theta. This is very simple. This is just taking a component of gravity. Now I'm going to do a small angle approximation, because you'll notice that this is not in the same form as f equals minus kx, because there's a sine theta here, and I want to get rid of that. So I've taken the approximation for small angles, because a pendulum is actually not simple harmonic motion. It's actually more complicated than that, because because of this sine theta thing. If it was theta, it would be simple harmonic motion. But what we can say is that as sine theta approaches 0, it becomes theta. And I've done a lot on this sort of thing before. This is the small angle approximation, so you might want to review that. I'm not going to go through that now, but I've done a lot of other videos about it. So, having said that in mind, when theta is small, we can say that fx is approximated by minus mg theta. I should have put approximately equal rather than equal here. So theta is equal to the length of the is equal to x over the length of the pendulum. Again, what that is basically saying that sine theta is equal to x over l, and so I've said that theta is equal to x over l here as well. It's basically just the approximation that I've been doing. Small angle approximation. Anyway, what I'm going to do now is now we have a relationship that we can work with. can say we've got an analogy. So we've got x here, which is the displacement in the x direction, and we can say that mg over L is sort of an analog of k. So using this relationship here, we can say omega is equal to root f over minus mx. I don't know what. Oh, yeah, okay, that's obvious. I don't know why I put that. So that's equal to minus mgx over L over mx. All I've done is I've substituted this into here. The mx and the mx cancel out, and we get root g over L. So yeah, that's a relationship that a lot of people know about.